Hello and welcome to the Sleepy Science Channel. I'm truly delighted you're here with me. Perhaps you've had a particularly long day, a day filled with its own little dramas and triumphs. Or maybe you're one of those inquisitive souls who finds peace in pondering the mysteries that lie hidden beneath our feet, beneath the familiar forests and open fields, beneath the vast shimmering oceans and towering mountain ranges, reaching down, down, down into the very heart of our Earth. Either way, tonight's journey is especially crafted for you, a tranquil passage designed to lull you into a restful sleep. There's absolutely nothing you need to do now except relax and let go. Allow your breathing to gradually slow, let your thoughts gently soften like wisps of cloud dissolving in the twilight sky, and allow your body to grow comfortably heavy, as if gravity itself is reaching out, gently pulling you downward through unseen layers of ancient stone and forgotten time. Because tonight, we're embarking on a quiet, deeply thoughtful journey, a pilgrimage, if you will, all the way to the very center of the Earth. We'll begin our descent at the sun-drenched surface, where life in all its vibrant glory unfolds under the watchful gaze of the daylight. From there, we'll slowly drift inward, passing through the Earth's rocky crust, descending into the deep, enigmatic mantle, and finally arriving at the ancient core, a place where molten iron moves with a liquid grace and where the planet's magnetic heartbeat mysteriously originates. We'll proceed slowly, gently, exploring just one quiet layer at a time, allowing ourselves to be completely immersed in the sensory details of each stratum. And just before we begin our descent into the Earth's embrace, if these calm explorations regularly bring you rest, if they offer a soft, comforting place to land at the end of your busy day, I encourage you to consider tapping the like button and subscribing to the channel. It helps other kindred spirits find their way here too, one sleepy soul at a time. Your support truly makes a difference. Now, let's begin. Close your eyes for a moment and picture yourself standing barefoot on the cool, receptive ground. Feel the surface beneath your feet. Perhaps it's the firmly packed earth of a winding forest trail, still bearing the faint scent of pine and damp leaves. Or maybe it's the smooth, weather-worn stone of a windswept mountain ledge, offering a panoramic view of the world. The air is still and calm, carrying only the faintest whisper of the wind. The stars above are distant and quiet, twinkling points of light in the vast, inky canvas of the night, and below you, extending far beyond the reach of your eyes, the earth stretches downwards, a hidden world of immense depth and mystery. Now, gently imagine beginning to sink. Not suddenly or abruptly, but slowly, almost imperceptibly, as if the earth itself were extending a welcoming invitation, gently pulling you in. You drift downwards through layers of rich topsoil and intricate tree roots, past shimmering glints of hidden minerals and ancient sedimentary layers. A pale fossil drifts beside you, a perfectly preserved imprint of a delicate leaf held captive in stone, a silent testament to a long-forgotten age. Then it's gone, disappearing into the darkness, and you're still sinking, gently, ever downwards. Beneath the world we know, the world of bustling cities and familiar landscapes, lies another planet, a planet within a planet, a hidden realm of untold wonders and unseen forces. Our Earth is layered like a complex story, told in chapters of immense pressure and intense heat. The crust, the solid ground beneath our feet, is just the beginning. A thin, rocky skin that floats atop something far more vast, far more ancient, and far more powerful. Below that lies the mantle, a dense, slow-moving ocean of solid rock so viscous that it flows over unimaginable spans of time, shaping continents and driving volcanic eruptions. And at the very center of it all lies the core, a hidden realm of molten iron and crushing pressure, where temperatures rival the surface of the sun, a realm we can barely begin to comprehend. We've never directly witnessed these inner regions. No camera has ever filmed them. No human hand has ever touched them. The deepest hole we've ever managed to dig, the Kola super deep borehole in Russia, only managed to penetrate the crust to a depth of just over 7 miles. But the Earth is more than 4,000 miles deep. Everything we know beyond that point comes from the faint echoes of earthquakes, from seismic waves rippling through stone like whispers in the dark, and from the shifting patterns of the magnetic field that protects our world from the harsh radiation of space. And yet, from these faint clues, a picture emerges, a vivid tapestry of heat, movement, and constant transformation. Deep inside, the Earth is vibrantly alive with motion. Rock flows like honey, molten metal spins with incredible speed, intense heat rises and falls in colossal currents, and slowly, patiently, this internal dance reshapes the surface of our world. Mountains rise majestically, oceans open vast chasms in the earth, continents drift across the globe, all because of the powerful forces hidden deep below. So, as we begin our gentle descent, you might find yourself wondering what exactly lies beneath us. What ancient processes stir in the impenetrable darkness? How does a planet manage to stay warm for billions of years? And why does the deep interior, a place we can never physically visit, hold so much power over the familiar surface we call home? These are the mysteries we'll explore tonight, quietly, gently, one layer at a time. Let's begin where we all live, on the crust, the outermost layer of the Earth, and the only one we've ever walked upon, the foundation of our existence. May feel solid and eternally stable beneath our feet, but the crust is actually thinner than we often imagine. If the Earth were a crisp red apple, the crust would be the skin, a fragile boundary atop a vast interior world. And this thin shell is not uniform across the planet. It comes in two main types: continental crust and oceanic crust, each with its unique properties. Continental crust is what forms the landmasses we inhabit, the continents themselves. It's relatively thick, averaging about 20 to 40 miles in depth, and is primarily composed of lighter granitic rocks, such as quartz and feldspar, the building blocks of many mountains. Beneath the oceans, however, the crust is quite different. Oceanic crust is significantly denser and much thinner, only about 3 to 6 miles deep, and is predominantly composed of dark volcanic rocks, such as basalt. This difference in density is one of the fundamental reasons why continents float higher than the ocean floor. The crust isn't simply resting on solid ground. It's floating slowly, imperceptibly atop the soft semi-fluid mantle below, like a raft adrift on a vast subterranean sea. And these floating plates of crust aren't fixed in place. They are constantly in motion. They drift, they collide, they break apart, and they reform over eons. This is the foundation of plate tectonics, the revolutionary theory that explains the dynamic movement of Earth's outer shell. The crust is broken into large interlocking sections called tectonic plates, which slide across the mantle like enormous puzzle pieces adrift on a sea of molten rock. These plates are in constant, albeit slow motion, typically moving only a few inches per year. But over millions of years, their seemingly insignificant movements shape the entire surface of the planet, creating towering mountain ranges, vast ocean basins, and dramatic volcanic landscapes. When two plates move apart, magma from the depths below rises to fill the void, forming new crust at mid-ocean ridges, like an underwater seam being perpetually stitched. This is happening right now beneath the Atlantic Ocean, where the Eurasian and North American plates are slowly drifting apart, widening the ocean basin bit by bit, a process that has been ongoing for millions of years. When plates move toward one another, the results can be far more dramatic and visually stunning. In some regions, one plate is forced beneath another in a process called subduction, a slow-motion collision of immense power. As it sinks into the mantle, the descending plate melts under intense heat and pressure, fueling volcanic activity and creating deep ocean trenches. This is why volcanic arcs, like those that form the Pacific Ring of Fire, often trace the edges of subduction zones, marking the boundaries of immense tectonic forces. In other regions, plates grind past each other sideways, creating transform boundaries, such as California's infamous San Andreas Fault. Here, the movement is not smooth and continuous, but jerky and unpredictable. Stress builds up slowly over time until it's suddenly released in a violent burst. And when that happens, the ground shakes, creating earthquakes that can reshape the landscape in an instant. This is the mechanism behind many of Earth's most powerful earthquakes. So while the crust may appear quiet and serene from above, it is anything but still. It is a dynamic shell in constant motion, fractured and reshaped by the slow, inexorable churn of forces beneath. Mountains rise where plates collide, like the Himalayas, which are still growing as the Indian plate pushes relentlessly northward into Asia, a collision that began millions of years ago and continues to this day. Volcanoes erupt along rifts and subduction zones, sending plumes of magma and ash soaring into the sky, a fiery spectacle of destruction and creation. and earthquakes mark the fracture lines where the accumulated stress of plate movement finally breaks free, releasing energy in the form of seismic waves. This restless surface has shaped not only the dramatic landscapes of our planet, but also the very history of life itself. The drifting of continents alters ocean currents and global climate patterns. It opens and closes migration routes for species, allowing them to spread to new territories or isolating them in unique environments. It brings different species into contact with one another or seals them off in isolation, driving evolutionary change in unexpected ways. Over geological time, the crust has written the epic story of evolution in rock and reef, in rift and ridge, a story that spans billions of years. And yet the crust is only the beginning. Beneath it lies a deeper engine, the mantle, that drives this constant movement forward. The crust is the outermost shell, but the heart of the Earth's motion lies deeper still, within the vast churning mantle. If you were to hold a small piece of the Earth's crust in your hand, a rough chunk of granite from a towering mountain range or a smooth slice of basalt from the ocean floor, you'd be holding a tangible record of Earth's formation, its complex chemistry, and its relentless motion. The crust is made of rocks, and those rocks are made of minerals arranged in intricate crystal patterns formed under immense pressure, intense heat, and vast spans of time. The most abundant elements in the crust are oxygen and silicon, which together form silicate minerals, the fundamental backbone of Earth's rocks. Quartz, feldspar, mica, and amphibole are all silicates, and they make up the bulk of the continental crust, forming its light-colored, relatively low-density foundation. These minerals are the primary reason why continents ride higher atop the mantle than the denser oceanic plates. In contrast, the oceanic crust is rich in denser iron and magnesium-bearing minerals such as pyroxene and olivine, which contribute to the dark hue of basalt and gabbro, the dominant rock types of the ocean floor. Granite, with its large, easily visible crystals and varied mineral content, dominates the continents. Basalt, fine-grained and dark in color, covers the vast ocean floors. Limestone and sandstone, formed from the accumulation of biological and sedimentary debris, add to the crust's incredible diversity, especially in shallow marine environments. And scattered throughout the crust are pockets of rare minerals, precious gems, valuable ores, and essential elements that have been concentrated by geological processes over millions of years. These are the veins of copper, the seams of gold, the deep pockets of lithium, and rare earth elements that modern technology so heavily depends on. But while surface rocks are relatively accessible, much of the crust lies far out of reach, buried beneath miles of rock and sediment. Understand what lies deeper, scientists have had to become incredibly creative, developing innovative techniques to probe the Earth's hidden interior. Drilling projects offer the most direct path downward, allowing us to retrieve samples of rock from previously inaccessible depths. Though even our most ambitious attempts have barely scratched the surface, they have provided invaluable insights into the composition and structure of the crust. The deepest hole ever drilled, the Kola Super Deep borehole in Russia, reached just over 7 miles into the crust after decades of painstaking effort. Temperatures and pressures at that depth became so intense that further progress proved impossible, and yet that narrow tunnel offered a remarkable glimpse into rocks more than 2 billion years old, formed long before the first complex life forms emerged on Earth. It was a window into a primordial world buried deep beneath our feet. Go deeper still, scientists rely on indirect methods, most notably the study of seismic waves, the ripples of energy that radiate outward from earthquakes. When an earthquake occurs, it sends out seismic waves that travel through the Earth like ripples in a pond. These waves travel at different speeds depending on the density and composition of the materials they pass through. Some waves can travel through liquids, while others cannot. Some bend and refract as they pass through different layers, while others bounce off boundaries like echoes in a canyon. By placing sensitive instruments called seismometers around the world, geologists can precisely track how these seismic waves move and use that data to infer the structure and composition of the crust and the layers below. Seismic tomography, a technique analogous to a CT scan of the Earth, allows scientists to build three-dimensional maps of crustal thickness, faults, and subduction zones. These detailed images reveal the boundaries of tectonic plates, the presence of buried mountain roots, and the slow, creeping movements of rocks many miles below the surface. With enough data, we can even see rising plumes of hotter mantle rock that may someday form new volcanic islands, giving us a glimpse into the planet's future. Other sophisticated tools help as well. Gravimetry measures subtle variations in the pull of gravity caused by denser or lighter rocks underground. Magnetometers track the subtle changes in Earth's magnetic field caused by buried mineral deposits, providing clues to the composition of the crust. And satellite imagery reveals surface deformations and uplift that hint at the powerful forces building from below. Together, these methods form a layered, multifaceted understanding of a world we cannot directly reach. We map the crust not with our hands or our eyes, but with echoes, fields, and data, slowly building a comprehensive picture of the Earth's restless skin. And yet the crust is not simply a boundary, an inert outer layer. It is a gateway, a dynamic interface between the Earth's interior and the world we inhabit. Everything above us, every towering tree, every majestic mountain, every vast ocean wave is shaped by what happens below. The crust is where geology meets biology, where deep Earth processes find expression in the landscapes we know and love. The crust may seem like a thin outer shell, but for life on Earth, it is everything. It's the stage on which the drama of biology unfolds, the surface that plants root into, the source of every essential element our bodies require, and the protective boundary that shelters us from the volatile forces of the deep. Without the crust, there would be no continents, no stable climate, no fertile soil to nourish forests, and no shelter from the intense heat that simmers far below. In its uppermost layers, the crust weathers slowly over time, broken down by wind, rain, and ice in a process that releases essential minerals that flow into rivers, accumulate in soils, and provide vital nutrients for plants and animals. Calcium, potassium, iron, phosphorus, all essential to life, come from the slow, patient erosion of rocks, a process that has been ongoing for billions of years. Even the carbon cycle, which regulates the planet's temperature over geological time, is tightly connected to the crust. Carbon dioxide from the atmosphere dissolves into rainwater, forming weak carbonic acid that weathers silicate rocks. The resulting minerals carry carbon into the ocean, where it eventually becomes part of limestone and other sediments. Over millions of years, plate tectonics lifts these sediments back up as new mountains, returning stored carbon to the atmosphere through volcanic eruptions. It's a long, slow cycle, but one that keeps the planet stable enough for life to thrive. Without the constant renewal and recycling of crustal material, Earth's atmosphere and oceans would become hostile and unbalanced, unable to support the complex life forms we see today. The crust also gives rise to the landforms that shape ecosystems and influence climate. Mountain ranges influence rainfall patterns and regional temperatures. Ocean basins control the circulation of ocean currents, distributing heat around the globe. Ridges, valleys, and volcanic islands create unique niches for life to evolve and adapt. Biodiversity flourishes in the cracks, edges, and margins of this dynamic shell, a direct consequence of the crust's uneven, ever-shifting nature. But even as we focus our attention on the crust, we must look deeper to understand why it behaves the way it does. The crust does not move on its own. Its restlessness is powered from below by the heat rising from the mantle and by even deeper forces originating at the planet's core. And one of the most profound links between the crust and Earth's interior lies not in rock or heat, but in something invisible and intangible: the magnetic field. Earth's magnetic field is generated in the outer core, where molten iron and nickel swirl in complex currents, creating a dynamic dynamo effect. This geodynamo produces a protective bubble, the magnetosphere, that surrounds the planet and shields it from the relentless solar wind, a stream of charged particles emitted by the sun. Without it, high-energy particles from the sun would gradually strip away our atmosphere, just as they did on Mars, leaving our planet barren and lifeless. Life on the surface, especially early life, may not have survived without this invisible barrier, and yet the crust plays a key role in how we understand this vital magnetic field. As lava cools and solidifies at the surface, iron-bearing minerals within it align themselves with the direction of Earth's magnetic field. These tiny compass needles become locked in place, recording the field's strength and orientation at the precise moment the rock formed. Over time, as tectonic plates carry these rocks away from spreading centers, We can read the magnetic patterns they leave behind like lines in a book that tell the fascinating history of Earth's magnetic reversals when the north and south magnetic poles switch places. Some crustal rocks are magnetized so strongly that they form local magnetic anomalies, subtle deviations in the magnetic field that reveal both the field's ancient behavior and the movement of plates over hundreds of millions of years. So, in this way, the crust is not just an outer shell. It is the crust. If you've the crust mountain beneath these volcanoes, each even the earthquake, every but to one, and so it's stretched. It is. This is while the beneath these changes slow the movement of material and affect how seismic waves travel, allowing geologists to map this boundary from afar, using seismic data to infer its depth and composition. Deeper still is the lower mantle, a zone of immense pressure where rock is hotter, denser, and more rigid than the layers above. Though it moves more slowly than the upper mantle, it still flows, carrying heat from the core toward the surface in a process known as mantle convection. This slow circulation of solid rock, driven by heat, is what keeps the Earth geologically active. Without it, the crust would fall silent, the plates would stop drifting, and the surface would freeze in place, becoming a static, unchanging landscape. Though we often think of the mantle as solid over long spans of time, it flows slowly but continuously, like an incredibly viscous fluid. This creeping motion is driven by heat, and it is the deep engine that powers the shifting of continents, the birth of new ocean crust, and the rise of great mountain ranges. The surface of the Earth may move just inches per year, but those movements are the result of immense forces rising from below, the steady convection currents of the mantle. Mantle convection is much like the boiling of a thick, heavy soup, slow, deliberate, and constant. Near the core, rock is heated to extreme temperatures, becoming slightly less dense and more buoyant. This buoyant material rises slowly toward the surface like bubbles in boiling water. As it travels upward, it cools, spreads laterally beneath the crust, and eventually sinks back down in cooler regions, completing the cycle. These massive cycles of rising and sinking rock act like a colossal conveyor belt beneath the tectonic plates, driving their movement across the globe. The plates themselves ride atop these currents, moving as the mantle flows beneath them. Where mantle material rises, we often find mid-ocean ridges, long underwater mountain chains where plates are being pushed apart and new crust is continuously formed. Where it sinks, we find subduction zones, where one plate is dragged beneath another and returned to the deep earth, a slow but inexorable cycle of creation and destruction. Even areas of seemingly quiet interior land can be influenced by this slow mantle movement, which can lift or stretch the crust over millions of years, creating vast plateaus or deep rift valleys. But what gives the mantle the heat it needs to move at all? What keeps this deep engine running? Some of the heat inside the Earth is primordial, a remnant of the planet's violent birth more than 5 billion years ago. As particles collided and merged in the early solar system, they released vast amounts of energy, generating tremendous heat. That heat has been slowly leaking away ever since, escaping through the crust and into space. Yet, if Earth had only that original heat, it would have cooled and fallen silent long ago, its internal engine grinding to a halt. What keeps the interior warm today is another, quieter process: radioactive decay. Certain elements found in Earth's rocks, including uranium, thorium, and potassium, are naturally unstable. Over time, their atoms break down into more stable forms, releasing heat in the process like tiny, incredibly long-lasting furnaces. This radioactive decay happens at a steady, predictable rate, and the energy it produces is immense. Though each atom releases only a tiny amount of heat, the Earth contains so many radioactive isotopes that together they contribute a significant portion of the mantle's warmth. Most of this radioactive material is found in the crust and upper mantle, where it continues to heat the surrounding rock, driving convection in the deeper layers. This way, radioactive decay acts like a long-burning fire deep within the Earth, a steady, patient source of energy that has powered the planet's interior for billions of years. It is this remarkable combination of leftover primordial heat and ongoing radioactive decay that keeps the mantle active and dynamic. Without it, the rock would grow still, the convection would stop, and the plates above would cease to move. There would be no new mountains, no fresh volcanic islands, no renewal of the crust. The very face of the Earth would change dramatically, not overnight, but slowly, imperceptibly, as the inner fire went out. But as long as these heat sources remain, the mantle will continue to flow slowly, powerfully, and invisibly, shaping the world above in profound ways. Not all the heat in the mantle rises as smooth, symmetrical convection cells. In some places, narrow columns of exceptionally hot material push directly upward from deep within the mantle, possibly from the boundary between the mantle and the core itself. These are known as mantle plumes, and where they reach the base of the crust, they can create persistent volcanic activity for millions of years, punching through the tectonic plates like a blowtorch through metal. One of the most well-studied examples of a mantle plume lies beneath the Pacific Ocean, responsible for the volcanic chain that formed the Hawaiian Islands, a testament to the power of these deep-seated forces. Like most volcanoes that are typically found gracing the edges of tectonic plates, the Hawaiian Islands stand apart, majestically situated in the very middle of the Pacific Plate. These volcanic paradises weren't forged in the fiery collisions of plates or the dramatic subduction zones where one plate dives beneath another. Instead, they owe their existence to a steadfast plume of scorching mantle rock, relentlessly rising beneath the ever-drifting plate. Imagine a blowtorch held against a conveyor belt. That's essentially what's happening. As the colossal Pacific Plate undertakes its slow northwestern journey over this persistent mantle plume, the plume stubbornly punches through the crust, birthing one volcanic island after another in a timeless geological dance. The Big Island of Hawaii, vibrant and teeming with volcanic activity, is the youngest in this chain, currently positioned directly above the hotspot, soaking in its geothermal embrace. Older islands like the serene Maui and bustling Oahu once held this prime position above the plume, but time and tectonic drift have carried them away, leaving them volcanically quiet, their fiery days now a memory etched in stone. Venture even farther northwest and you'll encounter seamounts, ancient submerged volcanoes now resting silently beneath the waves. They serve as poignant markers, tracing the languid trail of the plate as it journeys over the unwavering plume, a testament to the Earth's immense timescale. This volcanic breadcrumb trail isn't just a beautiful archipelago. It provides compelling evidence of both the relentless motion of tectonic plates and the dynamic behavior of the Earth's mantle. Reveals that the mantle isn't a uniform, homogeneous mass, but instead contains concentrated upwellings of intensely hot material that can persist for tens of millions of years, defying geological norms. Some scientists even theorize that these plumes may originate from the very boundary between the Earth's core and mantle, embarking on an epic ascent of more than 800 miles through solid rock before finally reaching the surface, an unfathomable journey. But the question arises, how can we possibly decipher what's happening at such inaccessible depths in a realm we can never physically reach? The answer lies in one of the Earth scientists' most invaluable and sensitive tools, seismic waves. When an earthquake unleashes its raw power, it sends vibrations rippling outward in all directions, much like the spreading circles on a pond's surface when a pebble is tossed in. However, instead of water, these waves surge through solid rock, carrying vital information about the Earth's hidden structure. These waves travel at varying speeds, dictated by the temperature, density, and composition of the material they traverse. By meticulously studying how these waves move, bend, reflect, and alter their speed, scientists can deduce the composition and characteristics of the deep Earth, unlocking secrets hidden for millennia. There are two primary types of seismic waves that act as our subterranean messengers. First, we have P waves, or primary pressure waves, which are the speed demons of the seismic world. These waves have the remarkable ability to travel through solids, liquids, and gases, making them invaluable for probing the Earth's core. Then there are S waves, or secondary shear waves. These waves are a bit more selective, only able to travel through solid material. This limitation, however, becomes a powerful tool in understanding the Earth's structure. When an earthquake sends these waves hurtling through the Earth, scientists can detect where S waves abruptly disappear. This disappearance reveals areas of molten rock or liquid metal, effectively mapping out the Earth's liquid regions. In the context of mantle plumes, seismic waves experience a noticeable slowdown as they pass through the hot rising material. This creates what scientists refer to as a low-velocity zone, a region where seismic waves are delayed due to elevated temperatures or partial melting of the rock. By meticulously mapping these low-velocity zones beneath known hotspots, researchers can trace the vertical shape and depth of mantle plumes, essentially creating a roadmap of these subterranean heat conveyors, using a sophisticated technique called seismic tomography.